Yeah, let's talk about graphing in 3D for a little bit, because even though we're going to move on to vectors pretty quick, it's important to have a working concept of how things in 3 dimensions work. So let's talk about graphing in 3 dimensions. We'll move on to vectors pretty quickly here, but it's important to know how the system works. So typically we have the XYZ coordinate system, something kind of like this. It is important that you plot these in the same way every time, meaning this axis point. So obviously, right, can't draw 3 dimensions actually on the 2-dimensional piece of paper. So we're projecting here, but this is the one that's supposed to be like pointing out at you. And this is the positive x-axis. This is the positive y-axis. This is the positive z-axis. It is okay to rotate things around if you need to, but this is an important but. Your coordinate system should obey what is called the right-hand rule, where if you put your right hand, right, don't be writing and do it with your left hand. That's called the right-hand rule for a reason. Put your right hand in the direction of the positive x-axis. Welcome, thank you. You curl your fingers towards the positive y-axis, and then your thumb should point in the direction of the positive z-axis. There is a left-hand rule as well for other things, but in fact, like there's some like video game orientations that use like a left-hand rule instead of a right-hand rule for the like physics, which is kind of neat. But as far as this class is concerned, right-hand rule is where it's at. So X, Y, Z, or you could like, sometimes it is convenient to rotate things in a way such that like X is pointing to the right, Y is pointing to the back, because that kind of looks like your usual XY orientation, just kind of like tilted back a little bit. And then your Z is still pointing upwards. And then of course we'd have the negative Y-axis this way, the negative X-axis this way, the negative Z-axis that way. So that's how we set things up. And we could plot points. So if I wanted to plot the point, say like 2, 4, 3, well, I have to kind of mark things off in an equal way. So here's another thing that's worth mentioning, and that is that the distance along the x-axis is not going to look the same as the distance along the y and the z-axis. So when I think about graphing things in 3D, the YZ plane is like the page. The YZ plane is the page you're on. It's like the back wall here. And then the x-axis, like if this is my origin over here in this corner, my x-axis is the line along the wall there that's on the ground. But when you've got this perspective thing, right, I can't draw those to be exactly the same because they get kind of shrunk. Like, right, if I take this pen that looks this long this way or this long this way, sorry if you guys can't see this one. Oh, I need to turn on my camera, sorry. Sorry, I should turn on my camera. Okay. Sorry, 1 second, I'll pin my video. Okay. So if you take this pen that's this long, or this axis that's this long, and then you do this to it, it doesn't look that long anymore. So these have to be a little bit shorter to give the effect of how things look the right way. So I'm going to plot the point 2, 4, 3. I'm going to go 2 in the x direction, 4 in the y direction. What I'm really going to do is I'm also going to go 4 in the y direction and then 2 in the x direction parallel. And then finally, I'm going to go 3 in the z direction. So I'm also going to go 3 in the z direction and then 2 in the x direction. So really, when I'm thinking about plotting a point, I'm kind of finding like the other corner of this box. So there's my point where I've gone 2 in the x direction, 4 in the y direction, and 3 in the z direction. Just some other things that occurred to me. In 2 dimensions, we have 4 quadrants. In 3 dimensions, we have 8 octants, but there's no real, there's no natural numbering, right? Like in 2 dimensions, we have first, second, third, fourth quadrant, and they go counterclockwise. In 3 dimensions, you have 8 octants, and we only really ever talk about the first one. So I would point out that the first octant, just like the first quadrant, is where X, Y, and Z are positive. There's a comma there. And someone could probably make a compelling argument for the 8th octant being where they're all negative. But other than that, there's no like second octant where one's, I mean, someone could probably number them if they wanted to, but we don't really do that. Let's talk about the coordinate planes. So the coordinate planes are, when you draw this XYZ coordinate system. Now, just like you can't draw an entire line, you can't draw an entire plane, right? It's infinite, so is a line, so we do our best. So here, and again, when I'm thinking of the XYZ coordinate system, I find it convenient to think of a room. So I really, if I'm standing out here in your perspective, I'm really thinking of that corner over there as my origin. So then up that wall there, up that line is my z-axis, that line over there is my x-axis, and that line against the bottom there is my y-axis. I just find that to be helpful in imagining things. So this XY plane, that's the floor. And the floor is when z equals 0. Right? You haven't gone up or down. Your height is 0. And then over here in the back, we have the YZ plane. Or as I would say, the board. The board is the YZ plane. It's the one you're looking at if you're thinking about looking at the system. And in the YZ plane, well, just like how in the XY plane, Z is 0, in the YZ plane, X is 0, right? You're on the board. You haven't moved forward. You haven't moved backwards. You're stuck here. You can move left, right, up, down, what you want. But you can't move forwards, backwards. And then over here on the left, right, on the wall with the windows on it. I know it's not perfectly flat, but you know, just imagine it is. Over here we have, of course, our XZ plane, where Y is equal to 0. I'm always imagining this is the plane that's like slicing out towards you. And yeah. Also, feel free to ask questions if you got them. So a plane typically is where, well, one of like the flat planes, I guess, is where one coordinate is equal to a constant. So either X equals a constant or Y equals a constant, Z equals a constant. These are kind of the planes we look at often, but there are also other planes. For example, if I go back to that point I had before, which was 2, 4, 3. So we look at this box here. This is where I have to be careful with my drawing. So notice that when I'm trying to find where like this line intersects what would come out this way, I'm trying to draw that parallel to the x-axis. Okay, so this top plane here, that plane is the plane z equal to 3. Because right, I'm got this is the point here, 2, 4, 3. So everything in that plane is at a height of 3. So z is 3. And in a similar way, this plane over here on the right. Oops, let's draw it correctly. This would be the plane x equal to 4. And this plane out in front here would be the plane y, let's draw it like this, y equal to 2. Oops, sorry, get a little off there. Something to think about with planes, or at least these planes, I should say, because these are not the only kinds of planes, right? These are just the ones that are kind of the easiest to draw, really, because they're flat or flat or flat. I mean, every plane is flat. Okay. Is that for these planes, the other two variables can be anything. Right? If you have the plane z equals 3, x and y can be any value. The plane x equals 4, y and z can be any value. It's kind of like drawing the line y equals 5. In 2 dimensions, the line y equals 5, x can be anything. Same idea here. Let's talk about spheres. Oh yeah, question. Yeah. Oh, you know what? Sorry, I said the wrong. Right. I even should have. Right. Yes, please. Yeah. Thank you. Someone wrote that in the chat too. I just didn't see it. Yeah, that should definitely be x equal to 2. Sorry. Well, this I guess this should be y equal to 4 is what it should say. This is really y equal to 4. Apologies. Yeah. And this is really x equal to 2, which we could have seen in 2 ways. One, this plane is parallel to that plane, so they should both be an x equals something. 2, this plane is parallel to that plane right, so they should both be y equals something. But I also should have pointed out that the y coordinate is 4, so I should have a plane of y equals 4. And at this point here, that all these planes go through, x has a coordinate of 2, so we should have x equals 2 as our plane. So yeah, good catch. Thank you. Please don't hesitate to, like, if you see me making a small mistake, please say it before I start saying crazy things. Let's talk about a sphere. No, let's talk about getting a new pen. This pen's like, the ink seems to like not want to always come out. So spheres are always fun to draw. And let's say the sphere has a radius of 3. So this point here is 0, 3, 0. That point there is 3, 0, 0. This point here is 0, 0, 3. Just to label a few of them. So what's the equation of this sphere? Sphere. It's always a word I struggle to say correctly. Well, just like a circle, all the points on the sphere have to be the same distance from the origin, or whatever the center is. So the distance formula in 3 dimensions still works exactly kind of like it does in 2 dimensions, meaning if you want to find the distance between 2 points, say x1, y1, z1, and x2, y2, z2, it's going to equal the square root of the difference in the x's squared plus the difference in the y's squared plus the difference in the z's squared. And so when I'm talking about a sphere, I want the distance between the origin and any point on the sphere to be 3. So what I'm going to say is the distance 3 has to equal the square root of, well, I want the distance between the origin and any point on the sphere, x, y, z. So I'm really going to have x minus 0 squared plus y minus 0 squared plus z minus 0 squared. Or squaring both sides, 9 equals x squared plus y squared plus z squared. That would be the equation of this particular sphere. And then more generally, the equation of a sphere is going to be given by x minus h squared plus y minus k squared plus z minus j squared equal to the radius squared, is the equation of a sphere with a center of h, k, j, and a radius of r. So when you see x squared plus y squared plus z squared equals something, that usually means you have a sphere. Or if you see x minus something squared plus y minus something squared plus z minus something squared equal to a number, you have a sphere. I was noticing one problem in the homework for the teacher that none of you appear to have, but there was one problem. It was like, what is the what is the equation x squared plus y squared plus z squared equal to 0 represent? And you might think it represents a sphere, and I guess technically it does, but it represents a sphere that has radius 0. So there's literally one point on the sphere, the origin. That's it. So it's kind of like a degenerate sphere is what we typically call that. So let's see. Describe a few other things. We'll move along. So what if I asked you to describe the following? Describe in space, meaning we have to think about, oh, thank you, all 3 dimensions. The set of points that satisfy the following. First, we'll talk about x squared plus y squared equal to 9. If as you coming just now, welcome. Here's the attendance form. We're just talking about some 3-dimensional graphing stuff. So normally you would look at this equation and you would think we have a what? Totally, it looks like a circle. And that's what we would definitely have in 2 dimensions. But in 3 dimensions, we have a third variable that essentially can be anything we want it to be. So this would be a circle in 2 dimensions. But then z can be anything. So that circle is going to get essentially stretched in the z direction, both up and down, meaning we're actually going to have a cylinder instead of a circle. Now, well, I'll say that in a minute. So this is actually a cylinder of radius 3. So drawing this, and again, here's where the drawing skills start to get a little challenging. I'm going to draw this circle of radius 3 in my XY plane as best I can. And then we're just going to make it go up and down. So now the thing is, technically this never ends, but I'm going to draw it like it does. But then I would maybe like draw some arrows pointing up like this and down like this to indicate, oh yeah, that's going to go on forever. And I guess I should maybe label that this is the point 0, 3, 0, and that's the point 3, 0, 0. Just to point out that, oh yeah, it is radius 3. But it's definitely a cylinder that goes on forever and ever and ever in the z direction. On the other hand, if I said we had the equation x squared plus z squared equal to 4, then I'd have a cylinder that extended in the y direction, because y is essentially y is free, is what we would say in this equation, y is a free variable. If y isn't occurring in the equation, it can be literally anything. So here, we're going to have a cylinder, but it's going to extend along the y axis. So I would try and draw a circle of radius 2 in the XY plane. Poorly, no, that's all right. And then extend it that way. What I really would probably do actually is draw the cylinder first and then like draw the little dashed part in the middle. That looks all right. And something I want to mention is that the word cylinder, when I say the word cylinder, when I hear the word cylinder, I think of one thing. I think of a circular tube. But a cylinder is actually named that really applies to kind of any shape that you extend in one direction. So for example, if I said I wanted to graph, say, maybe, I don't know, which one do I want to do here? Which one's the easiest to graph? Sure. Yeah. Sorry, this one's, I know it's always challenging. Let's say we want to graph z equal to y squared. This is also going to be a cylinder, even though it's not going to look like your typical cylinder. When we graph this, I always like the ones where it's just y and z because those are the ones where you're just like graphing essentially in the plane that you're used to drawing on. So if I graph z equal to y squared, yes, and I'm going to have a z-axis coming out at me in a minute. That's just going to look like your usual parabola. But then we're going to extend it towards you or away from you. So it's going now, and this is where I have to be extra careful. I'm going to essentially pick these points and then draw lines that are parallel to my x-axis. This might have been a time where it would have been better to maybe angle my x-axis more down. I'm going to try drawing it this way, and then I'm probably going to draw it again. So let's see. Let's use red. And then we're going to over here. And you're just going to try and essentially translate that down over here. So you're going to try and draw the same parabola. Like that. So you've kind of got, the way I kind of think of it is, I mean, you've got kind of like this parabola shaped piece of paper and it's coming out towards you. And it would also be going away as well. But that's also called a quote unquote cylinder. So don't get confused when someone says cylinder. Cylinder can really mean any 2D shape that you have extended in the third dimension. Yeah, there's lots of other things. I think that's good. Let's look at it. Let's see if there's anything on here that, yeah. I mean, let's do a couple more. Very, very good with this. Let's say we want to describe the set of points where we had x squared plus y squared plus z squared equal to 16 and x bigger than or equal to 3. Well, I know what that first thing is. It's a sphere. Then I'm like, what am I doing? I'm just saying x has to be bigger than 3. So I'm kind of taking this sphere of radius 4 and then I'm cutting off the back part of it, right? I'm kind of slicing it with this plane x equal to 3. Oh man, yeah. Like I would really love, so yeah, that's not my best work. So I will perfectly admit, and you should all be aware, drawing these things is not always easy. And it's something that's worth practicing. But as much as you practice, you might not always be. Some people are just also better drawers than other people. Like some of you are gonna be like surpassing me easily drawing these things. Totally fine. I'm not like worried about it. But what I'm trying to imagine here is like you've got, so I should have brought an orange. I should have brought an apple and a knife. Basically, you've taken your orange and you've sliced it this way, and you've taken the part that's in front when you've gone 3 out. So really, we're just kind of left with this kind of little bit of orange where this would still extend much, much further back to the entire sphere. And this picture is a little better because I heard some of you were like, oh, now I can kind of see what he's talking about. Right? We've got only the front little cap of the sphere because our sphere had a radius of 4. And then we went all the way out to 3 and then said, cut it and take the part where x is bigger than 3. If on the other hand, I had said the same sphere, but now x is, why did I pick x? X is like the worst choice I could have made. X is less than or equal to 3. Then I've got the other part of the sphere. I've essentially got my sphere dicey. And then right about here, I've cut it. Kind of looks like a Pokeball. Right? So I've cut off like the little front of the sphere, so there's like a little circle there, and you can see the orange, right? It's no, that's not, you should never cut an orange this way unless you're doing something strange with it, right? You're not going to get the orange the way you want it, but right, this essentially is flat. We're saying, okay, that's what we've got left. So this is the part that's covering that part up. And I know they don't look exactly the same, but that's the idea there. What else? I mean, a lot of this, so I'll say a lot of this is kind of just practicing self-discovery. It's something you have to do on your own to get a good kind of idea of what's happening. But I will say, there is definitely a tool you should all be aware of. It's linked in Canvas. It's the, but I'll show it to you all. I feel like we've looked at it before. It is the good one. Where'd you go? For real, the best. Yeah, that one. I had like two different links to it. I was like, this other one doesn't always work well. So this GeoGebra 3D thing, definitely a good place to go if you want to just kind of see what something looks like. So if you're trying to graph a thing and it's like kind of wonky, play around with this. It'll help you see what things are. So for now, the thing is, it is hard to do something like what we just described. Like if I wanted x squared plus y, oops, you also have to be careful and don't get your plus in the exponent there. I make that mistake all the time when I'm doing this. Oh my gosh, come on, plus sign, y squared forward plus z squared equal to 16. Cool, there's our sphere. You can totally like move it around, do all sorts of neat stuff with it. And then you can also graph the plane x equal to 3. And now you can see where that's slicing it. So right, there's the little front half that I was talking about and also the total back part. So definitely worthwhile. If you're trying to see what 3D things look like, you can usually do something to get close to what you're trying to graph, if not the entire thing. You might be able to do something funky with this one and say, I don't know if this is actually going to work, but you might be able to say something like, we want x to be bigger than 3. No, no, or maybe it just could be, no, I don't think so. It works in Desmos. There might be a way to do it. I haven't played around enough with it, but you might be able to actually get the thing you're trying for. But graphing the sphere and the plane, I think, is good enough to give us a visual of what we're trying to get out there. But I would encourage, I'm going to go play around with it now and see if I can make it work, because you can definitely do that in Desmos though. Like if you're trying to graph something in 2D and you want part of it, like for a piecewise function, you can totally put braces after it and say like x less than something or x bigger than something. Definitely works. Kind of neat. But I think that's enough about the 3D. I mean, we can certainly talk more about 3D graphing if you want, but we should probably start talking about vectors, because that's definitely the direction everyone is moving in. We're going to be talking all about vectors and kind of finding distance between things and angles between things and all the sorts of things. So let's talk about vectors. Yeah. And there's lots of different notation for vectors. So let's say we want to plot the vector. I'm going to write it in all the ways I might consider writing it. So here's one way you could write it. And actually, I'm going to write the vector that ends at the point that we were just talking about. The vector 2i plus 4j plus 3k. You could also write it in this notation 2, 4, 6. You could also write it in this vertical notation 2, 4, 6. People do all sorts of bonkers stuff. These are, in my opinion, the three, I'm going to be biased here, the three good ways of writing a vector. Some people who suck write it like this. I say don't suck, but this is not good notation for a vector because we also use this notation for points. So I would strongly encourage you not to use this. People also do use a, oh, sorry, I just started changing I changed my 3 to a 6 for some reason. I guess we'll use 6 because all the other ones are 6. Sorry about that. Some people also use this notation, which is a row matrix as opposed to a column matrix. This is also perfectly fine, actually. I would say this is not terrible, but this, I would really be like, no, we don't want to do that for our vectors. Okay, so if I'm trying to draw a vector, I'm really just going to go, let's see, 1, 2 in the x direction, 1, 2, 3, 4 in the y direction. I guess I'm going 6 in the z direction because I changed my vector. So let's see. I'm going to try to get out to that point over there. So I still need to kind of draw the things I was drawing before. I'm going to draw the little box situation here. I probably don't need to draw all of it. It's probably enough to do this, but let's do it anyway. I don't know why particularly I'm drawing these lines as dashed. They don't have to be dashed, but it feels like if you don't want a thing to actually be there, drawing it dashed feels more appropriate. And so then my vector, it's going to end at the point. So I'm going to write as a point 2, 4, 6. That's the point 2, 4, 6. Starts at the origin and ends, whoops, at that point right there, or close to it. So that there, that is the vector 2, 4, 6, or 2i plus 4j plus 6k. Some people like to put little hats or arrows over the ijk. You really don't need that. I mean, it's fine to do it, but it's kind of unnecessary. What to say about this vector? Many things. One thing is the vector doesn't have to start at the origin and end at the point 2, 4, 6. Usually when we're talking about vectors, that's the easiest way to draw them because we can always locate the origin really easily and then draw the vector from the origin to the point we want to end at. But technically any vector that started at a point and went 2 in the x direction, 4 in the y direction, and 6 in the z direction would be the same vector. Not just equivalent, really the same. Because the vector is just a length and a direction. So if two vectors have the same length and the same direction, they're the same vector. Speaking of length, what is the length, also known as the, probably preferably known as the magnitude of the vector v equal to 2, 4, 6. Well, we just talked about the distance equation. The length of a vector is literally the distance from its originating point to its terminating point. But since this is again why it's convenient to think of the originating point as the origin, because then you have to say, well, the length of this vector is just going to be the square root of the first coordinate minus 0 squared. Well, I don't need to subtract 0. I can just be like it's 2 squared plus the second coordinate minus 0 squared plus the third coordinate minus 0 squared. And instead of calling it the distance, we're going to use, some people use single, some people use double. Most people use a double bar for this for magnitude of a vector. Although you will certainly see people write it as an absolute value and still mean magnitude. It's technically not an absolute value because you're not just taking the absolute value, you're finding the length of it. But they're very, very closely related. This would end up being the square root of 4 plus 16 plus 36, which I would probably leave that way. Okay. What is a unit vector in the same direction as v? Unit vector just means a vector of length 1. And so when you want to find a unit vector in the same direction as your original vector, you take your original vector and you divide it by its length. So generally, the unit vector in the direction we want is, we often call it u, and it's just v divided by v's own magnitude. I should clarify that if someone ever asks you to get, like someone says, what direction is this in? I might say it's the vector 3, 4. Because I went over 3, not for this, right? For like general example. I'm gonna move around the board for a second. You guys can all hopefully see that too. Saying like a real man. Sorry. No, I don't think it's over. I think I just blew it somehow with the pulling the cord out here. Now it's sorry, 1 second. Apologies. Wow. Okay, I think okay. Are the Zoom people still there? I think so. I see you there. I think we're all right. Let's but I did definitely, 1 second. Sorry. Wow, really blowing it. Okay, it's okay. I'm blowing. Oh, there we go. Okay, back over here. Cool. What I was gonna say on the chalkboard over here, which I think you all can see, and I'm not gonna touch that anymore, is that if someone said to give me a vector in the direction, also known as a director, not really, in this direction, which I'm going to say is over 3 and up 4. Someone might say, well, a vector in that direction is the vector 3, 4. And I wouldn't think they were wrong. They might also say a vector in that direction is twice it. Let's call it W. It's 8. Someone else might say it's, I don't know, something else. I don't really care. Like Q equal to 300, 400. Technically, we'd all be right. All of these vectors in the same direction. Well, we don't like asking questions where there are lots of right answers. So especially web work. If you not like Tab's class, I know you guys aren't really using web work, but web work really doesn't like that. So if someone asks you what direction is this vector going in, and they want everyone to give the same answer, the answer that we're all going to be expected to give is the vector that has a length of 1, a unit vector. So the correct answer, the direction that this vector is going in, is this vector, or any of these vectors actually, divided by their own magnitude, which in this particular case is the vector 3, 4. And help me out, what's the magnitude of the vector 3, 4? Everyone's favorite Pythagorean triple. Right, the magnitude's 5. Right, you went over 3, up 4, the hypotenuse is, oh yeah, it's 5. So the answer that's correct is that the vector in this direction that we're going to say is the direction vector is the vector 3/5, 4/5, because that's the vector of length 1. So when someone asks for a direction vector, they usually mean give me a unit vector as your response. So whatever your direction is, divided by its own magnitude. Hopefully you guys can see that all right.
Is the I was wondering sure, like obviously like for the on you did on the chalkboard, the vector 8 is like constants on there, you just have like the double.
Oh yeah, see, right? I took right. Yes. I also fall prey to writing the magnitude of a vector using just a single thing, because most people are totally fine with it either way. But yeah, so you'll probably see, you might see your teacher use either one. In this particular question, the vector I'm looking for would be this vector 2, 4, 6 divided by the square root of 56. And I don't feel a need to actually distribute that division by root 56 to each term, but you certainly can. You can definitely write it as 2 over root 56, comma 4 over root 56, comma 6 over root 56, or even 2 over root 56 I plus 4 over root 56 j plus 6 over root 56 k. And you can probably rationalize and do other things that aren't that important. So we have the following observations. Vectors, as I said before, have a magnitude, aka a length, and direction. Examples of this that you are probably aware of already are velocity and force. So, question, yeah. Yes. Right. So because the difference here is this is a 2-dimensional vector and that was a 3-dimensional vector. That's why. But yeah, so so not that we do this in this class, but how many of you are planning on taking Math 22A at some point? I imagine most of you. So the thing is, we start talking about vectors in more than 3 dimensions. And even though physically that might not make a lot of sense, it sure doesn't to me, but you can still extend these definitions. So you can talk about the length of a 4-dimensional vector by just taking the square root of the first component squared plus the second component squared plus the third component squared plus the fourth component squared, or however many dimensions you want. So when you're talking about the length of a vector or the it really does make more sense to talk about magnitude in that sense because it can kind of be broader. We're really just extending this definition to more dimensions. So just to kind of continue, the vectors have magnitude and direction, whereas scalars, when you hear the word scalars, you should just think real numbers, right? 5, -2, pi, etc. Scalars are just magnitude. So what's the just magnitude component of velocity? Speed. So, right, if I say I'm going 50 miles an hour, okay, I've told you my magnitude. If I told you I'm going 50 miles per hour headed west, I've given you a vector because I've told you direction and speed, or direction and magnitude. Force is never my favorite. When you think of force, you should think of, well, okay, I shouldn't be so prescriptive. When I think of force, I think of weight. My weight in pounds is a force. My weight in kilograms isn't a weight. My mass is measured in kilograms, and my weight in the metric system is measured in newtons. Kilograms times the gravity, the acceleration of gravity. So magnitude is just mass. So mass is, and then force is mass times acceleration. Acceleration has a distance, a direction associated with it. So, right, when I talk about my mass, I might say, I don't know, like I have a mass of 80 kilograms, for example. Whereas I would say my weight is 80 times 9.8, whatever that number is, in the direction of towards the earth, because my force is towards the earth. So force has a direction. Mass does not. Mass is just a description of how much space we are taking up. I mean, I guess you would say that's volume. Okay, it's mass density. Right. I don't want to get too physicsy here. Yeah, it is interesting, right? Kilograms is actually a measure of mass. This is a measure of weight. In the US system, it's terrible. Pounds is a measure of weight. And does anyone know the measure of mass in the US system? Not pounds. Pounds is all, well, yeah, pounds is, I think, I thought I just said pounds. Did I not say pounds? Pounds, so pounds is a measure of weight. Mass, that's metric. Mass is measured in, it's the, what's the thing I'm looking for? It's the mascot of UC Santa Barbara. Does anyone know the mascot for? It's a slug. Right? Oh, did I mess it up? I don't know my mascots. Which one is that? Santa Cruz. I almost got it right. So yeah, UC Santa Cruz, they're the banana slugs, right? And mass in the US system is measured in something called slugs, which is a terrible unit, but whatever. It is what it is. Take physics, you'll get to learn all about it. It's fun if you like that kind of thing. So, adding, subtracting vectors. The nice thing about adding, subtracting vectors is it essentially works how you would want it to work. Meaning, if you have the components of two vectors and you want to add them together, you just add the components together. So for example, if we have, so even though we're going to move the work mostly in 3 dimensions, I'm a much better drawer in 2 dimensions. So we're going to use some 2-dimensional examples and extend the idea to 3 dimensions. So let's say we have these 2 vectors, u equal to 3i plus 1j and v equal to I plus 5j. God knows why people picked U and V. It's kind of like the worst choices we could make because they, at least when I'm writing them, they start to look the same. So you can pick other names, but U and V kind of became standard for some reason. I want to find U plus V. I can just add the components. So I'm going to get 3i plus I, which is 4i, and j plus 5j, which is 6j. Now, there is a nice graphical interpretation as well. If you take, and this is where I should be very kind of careful with my numbering here. So let's see, U is 3i plus 4j. So I'm going to go 3 in the x direction, right? I is the, so I should point out, I is the unit vector in the x direction. J is the unit vector in the y direction. Or if you're in 3 dimensions, I is the unit vector in the x direction. J is the unit vector in the y direction. K is the unit vector in the z direction. We would say that these i's are the same because they both go 1 in the x direction. Just this one, you didn't write the third component of it. So if I'm going 3 in the x and 1 in the y, I'm going over 3 up 1. So I'm going to end here. There's my u vector. On the other hand, v, I'm going over 1 and up 5. There's my v vector. And then what we can do to get u plus v is we can put the beginning of u at the end of v, or the beginning of v at the end of u. As we say, we like to go head to tail. So I'm going to start here and I'm just going to put v over there. So I'm going to go over 1 and up 5. And there, my friends, we have u plus v. Or, if you prefer, v plus u. Same thing. Just like with regular numbers, I should say, just like with scalar numbers, order of addition doesn't matter. U plus v equals v plus u. Most, but not all, regular operations mathematically still work the same way with vectors. Not all of them. And then we can also find u minus v. U minus v to me, well, is easy to calculate. U minus v is going to be 3 minus 1i, so 2i. J minus 5j is minus 4j. Graphically, I always struggle to remember how you're supposed to do this one. So I always just draw it out. So I want u minus v. So I'm going to go in the u direction. So there's my u vector again. And then what I want to do is I want to add negative v. So I'm going to, instead of going over 1 and up 4, I'm going to go back 1 and down 4. So I'm going to go back 1, down 4. There's my negative v. So this vector here is u plus negative v, which is u minus v. And after I do that, then I'm able to do the actual trick, which people like to do. So another way you can do this instead of drawing u and the minus v is you can draw u normally. You can also draw v normally, meaning when I say normally, I mean starting at the origin, which is kind of the normal way we draw vectors. So I go over 1 and up 5. And then if you go from the end of v to the end of u, that vector is also u minus v. I always find that tricky, but if you look at it this way, we're like, yeah, that vector and that vector are the same. They both go in the same direction. They both have the same length. So if you're trying to draw these things, not that we do a lot of this, if you really want to draw u minus v, you're like, okay, I'm going to draw u, I'm going to draw v, I'm going to start at v, I'm going to end at u. And that's, which makes kind of sense, right? If you start somewhere and end somewhere else, you're doing that one minus that one. It makes lots of sense now that I say it out loud. All right. So, oh yeah, we got lots of time. How do we multiply vectors? Well, I would say that there's 3 ways, although only 2 that we really care about. So the first thing that I'm actually referring to is you can multiply a vector by a scalar. So for example, we can take the vector 3, 1, 2 and multiply it by any scalar you want. So 5 times the vector v is just 5 times the vector 3, 1, 2. And not surprisingly, it multiplies each component by 5. Wow, can I multiply by 5? Yeah, I can. Not very exciting. I should mention that when you multiply a vector by a scalar, you're going to multiply its length by that scalar. So whatever length this vector has a length that's 5 times as much. And that's kind of not terrible to see. If I wanted to find the magnitude of v here, the magnitude of v would be the square root of 3 squared plus 1 squared plus 2 squared, which is going to be the square root of 9 plus 1 plus 4, which is 14. This magnitude of 5v would be the square root of 15 squared plus 5 squared plus 10 squared. But I should be smart about this. I can factor out a 5 squared from each of those. If I factor out a 5 squared from 15 squared, I'm left with a 3 squared. If I factor out a 5 squared from there, I'm left with a 1 squared. If I factor out a 5 squared from there, I'm left with a 2 squared. And then I'm ending up with the square root of 5 squared times 14, or 5 times the square root of 14. So, oh yeah, when you multiply a vector by a scalar, you're multiplying its magnitude by that scalar. Okay. But then we have really the things we actually care about. We have what's called the dot product, also sometimes called the scalar product, although I've really almost never heard anyone call it that. It's called that because the output ends up being a scalar. And we also have the cross product, also sometimes called the vector product, because the output ends up being a vector. So when you dot 2 vectors together, you get a number. When you cross 2 vectors together, you get a vector. Let's talk about what this is. So one way of calculating the dot product of 2 vectors, u and v, is that u dot v is equal to, I need to draw a picture first, sorry. Here's u, here's v. U dot v is equal to the magnitude of u times the magnitude of v times cosine of the angle between them. I should say cosine of the angle between them is less than 180 degrees, meaning I shouldn't measure the angle around this way. That would be silly. Always the angle that's less than 180 degrees, or less than, or equal to, I suppose, 180 degrees. Cross product later. It's not that bad. I mean, it's not that bad when it's like 2 dimensions. It's a little worse when it's 3 dimensions, but it's really not as terrible as someone might have made it out to be. Then there's a couple of ways of thinking about it, but I should point out, so this is going to give you a number, whereas when you take the cross product of 2 vectors, it's going to give you a third vector that's perpendicular to the other 2, which is kind of neat. And that's actually where the right-hand rule is going to come into play. If you take u and v and you cross them together, you put your, so, and this is, so it's interesting. I know I'm saying the thing we're saying later, but if you have u and v, the order you cross them in definitely matters. If you do, like if this is my vector u and this is my vector v, if I do u cross v, right-hand rule says my vector is going to point that way. On the other hand, if I do v cross u, I'll put my fingers in the direction of the first one. I curl them towards the other one, and then my thumb points in the down direction. So the order you cross things in actually, if you do it the other way, changes the sign. So it's called an anti-symmetric function. Kind of change. Whereas the dot product totally is the same every time, meaning u dot v is equal to v dot u. Which if we look at this calculation, makes sense. Shouldn't matter what order I do it in, the magnitude of u doesn't change, the magnitude of v doesn't change, and cosine of the angle between them isn't going to change. So order of dot producting doesn't matter. So let's look at some examples to help us see the easier way of calculating a dot product. Let's say that u is equal to 2i and v is equal to 3i, which I know is not very exciting. So here are my vectors, 2i and 3i. All right, u dot v is going to equal the magnitude of u times the magnitude of v times cosine of the angle between them. What's the angle between these two vectors? Well, they're pointing in the same direction. So the angle is, there isn't one, right? 0. There's 0 angles that point in the same direction. So that's going to be, well, the magnitude of 2i is just 2. Right? If the vector only points in one direction, you can just take the coefficient of it. Well, I should say the absolute value of the coefficient of it to get the magnitude. So the dot product here is 6. And it would be the same, I should mention. Would it be the same? No, it wouldn't be the same. So just to kind of see the other way, what if u is equal to negative 2i and v was equal to still positive 3i? Then my vectors look like this. Here's v. There's u. And u dot v is going to equal, again, times cosine of what? What's the angle now? The angle is 180, or pi if you prefer, which we kind of do prefer before. So the magnitude of u is still 2 because it has a length of 2. Right? Magnitude is always a non-negative number. Magnitude of v is 3, but cosine of 180 is negative 1. So the dot product of these two vectors is negative 6. All right, and then thirdly, what if u is equal to 2i, but v is equal to 3j? Well, what's the angle between these two vectors? It's looking pretty 90 degree-ish. And what's cosine of 90 degrees? So if we do this, you can see how people might start using single things because it gets to be like, you're okay, I'm writing like a million little things here. I think we're going to get 0 because I'm going to get 2 times 3 times cosine of 90. Oh, that's 0. So later on, someone might ask you, how can you tell if these two vectors are perpendicular to each other? And the answer is going to be, oh, is their dot product 0? The dot product 0, the vectors have to be perpendicular, or orthogonal is another word we use. And if the vectors are orthogonal, their dot product has to be equal to 0. So let's look at a less a less straightforward example maybe. Let's say we have the following. Let's say we have u equal to 2i and v equal to 3i plus 4j. All right, so I'm going to draw this. So here's my u, 1, 2, and v is going to be over 3 and up 4. We picked 3, 4 because we know the magnitude of it. The magnitude is definitely 5. So here, u dot v is going to equal magnitude of u, magnitude of v, cosine of the angle. So the magnitude of u is definitely 2. We just found the magnitude of V. It was 5. Oops, times cosine of that angle. Well, the angle, if we draw the little triangle here, if that vector is the vector V, then we went over and up how much? We went over 3 and up 4. Hypotenuse is 5. Cosine of that angle, we can totally find using like regular trig stuff. Cosine is adjacent to hypotenuse, which is going to be 3/5. 5's cancel and we get 2 times 3, which is 6. So this kind of hints at does each variable after the coefficient represent a different direction? Yeah, so the I direction is the X direction. So I is the X direction, J is the Y direction, and K is the Z direction. And I wouldn't necessarily call them variables so much as I would call them unit vectors in the different directions. Because they're really not variable, they don't change. I is always the unit vector in the X direction. J is always the unit vector in the Y direction, and K is always the unit vector in the Z direction. So this kind of actually hints at a more convenient way of finding a dot product, because this is fine if you can find the angle between them, or if you can find the triangle for the angle between them. But if you've got two vectors like where one of them isn't on the x-axis or one of the axis where it's convenient, it can be really hard to be like, what's the angle between those two vectors? So there is a way of doing this. If u equals the same one here, 2i, and I'm gonna say it's 2i plus 0j, and v is equal to 3i plus 4j, the dot product of u and v can be calculated by multiplying the common coefficient components together and adding up the results, meaning it's going to be 2 times 3 plus 0 times 4, which is also 6. And it works for any vectors. If u is equal to 2i plus 5j and v is equal to 6i plus 3j, then u dot v is simply calculated as 2 times 6 plus 5 times 3, which is 12 plus 15, which is 27. You could probably, if you tried really hard, draw some vectors and draw some triangles and probably find the angle, or at least probably find the cosine of the angle between them, but it's not worth the effort. Not when we have this much easier way of doing it. Sure. Here's a work problem. Some physics. Oh my gosh, can I write words? So remember, maybe you remember, we did some work calculations in 21B. Maybe. We did like some integrals of like moving some water or something, or a spring, or a bucket that leaked. Anyway, this isn't that, which is good because those problems they're fine, but like, they get to be a bit much. Let's say we've got this. A force of 100 newtons is applied. Yes, I can. Thank you. In the direction of the unit vector u equal to 3/5 I plus 4/5 j, and it moves a box 10 meters across a horizontal, or I could say level, floor. How much work was done? Well, let's take a look. Here's our horizontal floor, the x-axis. Here's our box. And we're applying a force in not quite right. So it would probably make the most sense to just apply the force like straight on in the direction we want to move. That would give us the best, return on our effort. But maybe we're like up high and we're pulling the box on a rope or something. It's not exactly clear why we're doing it this way, but we are applying a force in this direction. There's some angle there. We may or may not need to know it. So our force as a vector is going to be the 100 newtons of force multiplied by the actual direction that it's in. 3/5 I plus 4/5 J. And multiplying that out, that's going to give you a force of 60 I, not J, plus 80 J. All right. Only the component of force that's in the same direction as the direction we're moving, right? So we're going to move this direction, and we're going to move 100 in that direction. So that's the vector that's in the direction that we're moving. So we want to know how much work we're going to do by finding how much force is applied in the direction that we're moving. Essentially, what we're trying to do, in fact, let me write that. I get in this bad habit sometimes of saying words and then not writing them down. So let me write them down. So only the component of force in the same direction as D will contribute to work. As a reminder, the one thing I was trying to say about work, about all the things that were wonderful about it, is work is force times distance. And I feel like if you remembered anything from 21B about work, you remember that the work is a force times the distance. So we're trying to figure out what our force times distance here is, but it's only the force in the direction we want. So we're going to say, well, the work is going to be our force vector dotted with our distance vector, which is going to be, well, we got 60I plus 80J dotted with our distance vector, which is 100I plus 0J. Not that you really need that. And you're going to get 60 times 100. For some reason, I'm missing a 0 there. Oh, no, I'm not missing. I see. I'm not missing a 0 there. I'm added a 0 there. Right, I got my 100 and my 10. That should be a 10I, not a 100I. Sorry about that. So that should be a 10, not 100. So 60 times 10 is 600, plus 80 times 0 is 0. So that's going to be 600. 600 watts. If we're doing work, and we're in the metric system, our answer is in Newton meters, also known as joules. So the other thing that, okay, let's get a paper cut. Not really, I didn't get a paper cut, but my nail almost got a paper cut. The other thing that I think is maybe interesting about the dot product. So interestingly, we can use the dot product to find the angle between any two vectors. And this is true in 2 dimensions, in 3 dimensions, actually in any number of dimensions you want. So you can talk about finding the angle between two vectors in 5 dimensions. It's not hard. It's not easy to like visualize what's going on there, but it is something that is very, very easily calculatable, which is kind of weird. But we're just going to take our dot product equation, u dot v equal to the magnitude of u times the magnitude of v times cosine of theta, and solve for theta. So I'm going to divide both sides by the magnitude of u and the magnitude of v. And then take the inverse cosine or the arc cosine of both sides and say, oh, it's going to give me theta equal to the arc cosine of this mess. Personally, if I was going to remember one of these formulas, I would remember this one. because it just seems easier to write. I don't like writing on arc cosine unless I have to be frank. But this is how you can always find the cosine of an angle between two vectors, or how you can find the angle between two vectors. So for example, what's the angle between the vectors 2i plus j minus 2k and v equal to 3i plus 0j plus 4k? No need to write the 0j there, right? Like if someone wrote 3i plus 4k, the assumption is the component of j is 0. I'm out of water. All right, well, let's find all the things. The magnitude of u is the square root of 2 squared plus 1 squared plus negative 2 squared. Oh, that's convenient. That's 3. The magnitude of v is obviously 5. You're going to see a lot of 5s. Like, there's going to be a lot of, maybe not a lot, but a fair amount of 3, 4, 5s in your future when you're finding magnitudes. And then we can say that I'm going to write it this way. Cosine of theta is equal to u dot v over the magnitude of u times the magnitude of v, which is equal to, let's see, u dot v is going to be 2 times 3 plus 1 times 0 plus negative 2 times 4 all over 3 times 5, which is equal to 6 minus 8, which is negative 2 over 15. So then our angle theta would equal the arc cosine of negative 2 over 15. Or if you prefer, the inverse cosine of negative 2 over 15. Now, I would need a calculator to find this, but I will point out, we know for sure that this angle is bigger than 90 degrees, or it's between 90 and 180 degrees. Because if you're taking the inverse cosine of a negative number to get an angle, that angle had to have been in quadrant 2, not quadrant 1. So it's equal to something. Equal to, use a calculator. Okay, let's do one more. Okay, we'll talk about projections next time. So this one I think is kind of interesting. This question does or could come up in chemistry. It's kind of neat. Find the bond angle between the carbon and one of the hydrogen atoms on a methane molecule. Which is CH4. And has a tetrahedron. It's a tetrahedron with carbon in the center. So here's what it kind of looks like. So, yeah, I'm going to draw my tetrahedron. I'm first going to draw a cube. We have enough time. We have enough time. We can do this. Yeah. So I don't know a lot about chemistry, but I can certainly draw a tetrahedron. You may be like thinking, James, that looks a lot like a cube and not like a tetrahedron. I say, okay, calm down. I know it looks like a cube because it is a cube. But a tetrahedron, you can say, well, tetrahedron, I'm going to connect this point, this point, this point, and this point. And that gives you a tetrahedron. Come on. There's your tetrahedron. Maybe not my best drawing ever, because okay, but you can kind of see it, right? A little bit. Okay, and if I make the corners of that, I can be smart about this. I'm going to say this cube. I'm going to change it. Yeah, okay. Let's say this is at the point 0. Sorry, not 0. 2, 2, 0. Right, and this is at the point 0, 2, 2. This is the point 2, 0, 2. And so the point in the middle, right? These are all the hydrogen atoms. And then the point in the middle right here is my carbon. And so I'm trying to find the angle right there. Right. And that point in the middle of my cube is the point 111. Neat. So here's what we've actually got. We're trying to find this angle. That point there is 1, 1, 1. That point there is 2, 2, 0. And that point there is the origin. So my vector u, oh, that's it. This actually brings up something worth, oh man, it's at 259. I agree, yes. So real quickly here, my vector u is the vector -1, -1, -1. Because I'm starting here and I'm going there. To find a vector, if you're given 2 points, you take your terminating point, you subtract your initial point. My vector v is the vector 2, -1, 2, -1, -1. Right? That. And then the angle between them, well, let's find the magnitudes. The magnitude of u is going to be the square root of 3. The magnitude of v is also the square root of 3. Right? Square root of 1 plus 1 plus 1. And then finally, cosine of the angle between these two vectors is going to be u dot v. So let's see. -1 plus -1 plus 1 all over the magnitude of u times the magnitude of v, which is going to end up being -1/3. So the angle between these two vectors, aka the angle between the carbon and one of the hydrogen atoms, is going, or 1? I mean 1, okay, sure. Is going to be, I think you should say 2 there, really. That's going to be the inverse cosine of -1/3, which is approximately 109.5 degrees. Or as someone pointed out, it's way cooler to say the arc cosine. So it's the arc cosine. I agree. Arc cosine does sound cooler. Sounds like you're more mathy. So interesting. If you have a methane molecule, the angle between one hydrogen to the carbon and the other to the carbon is about 109.5 degrees. Kind of cool. All right, I should stop. It's 3:01.